Let's start. So this class, we will be seeing application of what we've learned so far, the three theories of failure of ductile materials. So the question is, how do you choose a theory for applying or designing a machine? What you can do is you can take different materials. So here there are 4 of them which are shown, and stress it up, right? Keep increasing the stress in tension, and then when it fails, figure out what the stress at which it failed, and then put that stress on this plot, which is basically the principal stresses in the x-axis, right, and y-axis, sigma 1 and sigma 2, and it's sort of non-dimensionalized by dividing by the shear strength. Okay, and so if those points which I've shown you, the dots, if they lie on the envelope for the distortion theory, then it means that that would be a better predictor of theory than the other theory, maximum shear stress theory. So here, in fact, it looks like many of these points actually lie on this envelope, right? Which happens to be this is also known as distortion energy, or von Mises shear. Okay, and this one is our maximum shear stress theory, tau max. So only a few points actually lie on this curve, on the max shear stress line, but many do seem to lie on the distortion energy theory. Now, there are some points here you can see they're a little bit problematic because they just tell you that the material here fails much before it reaches this envelope, right? So really what this is saying is you better be a little bit more conservative. You better apply the factor of safety when you design things. Don't really use the shear strength and this theory to design a material. So always we keep some factor of safety, so our actual envelope is actually going to be shrink by that amount. Okay, so what we'll say here is many points lie on D then rather than MSS. This is MSS, hence DE is a better predictor of failure. So given a choice, you want to probably apply the D. These plots are also points are only for materials that behave the same way in tension and compression. That behave, or rather fail, the same way in tension and compression. Okay. If at all you come across a situation where it's a ductile material indicated by the curves, there's a distinct failure point which is different from the ultimate strength and yield point, and you see that the strength in tension is different from the strength in compression, then you want to use the Mohr Coulomb theory. If strength in tension is different than the strength in compression, The recommendation is use Coulomb-Mohr theory. Coulomb. Okay, so with that, let's get into problem solving. I shared a file earlier today of few problems I'm going to solve in class. Okay, I'll go with those and I'll try to finish all of those so that we are done with this part. So let's get to the first problem. Okay. So the critical load that leads to a failure is shown, assuming SY is 250 MPa. Find the factor of safety when yielding, assuming maximum shear stress theory, maximum distortion energy theory. What really is happening here is that we've identified the point on the machine element which is failing, and we've drawn this failure, the stresses for that critical point with this cube. Okay. Now, with this information in mind, the question is, can we find the factor of safety using these theories? Okay, so it's sort of application of the maximum shear stress and distortion energy to a particular stress or loading condition.
This must be a 40 or 90 on the top.
It's 40.
Thank you.
Okay, so before we apply any of these theories, let's see what we really want to know. From the shear stress theory, we know that we want to find the maximum shear stress. And for distortion energy theory, we want these principal stresses, sigma 1 and sigma 2, right? And so first thing we can do is find the principal stresses from the diagram. And then once we have that, we can proceed and solve for the failure theories and then factor of safety. So let's find the principal stresses. Okay, so at your disposal, you can, two methods. One is you can use the Mohr circle to find the stresses. We can also use the formulas, which I derived. We can sort of use a combination. So what we need is essentially the center, right? And then we need the radius. That figure. So if we know the center and radius, we can find sigma 1 and sigma 2, right? It's basically the center plus or minus radius will give me sigma 1 and sigma 2. So let's just find this radius and center of the circle. So the center is given by sigma x plus sigma y divided by 2 comma 0. And so that is equal to, so it's sigma x is 80. Sigma y is minus 40 because it's compression divided by 2, 0. And so the center is at 20, comma 0. Okay, so the radius is, and I'm going to use the formula here, it's square root of sigma x minus sigma y divided by 2 square plus tau x by square, right? So that comes out to be 80 minus 40 by 2 square plus the shear stress is 25. And so that comes out to be 65. Okay, so that's basically pretty much application of the formula. So now we're in a position to find the principal stresses. Okay, let's just call that sigma A and sigma B, just to be true to the notation we've used in the second part about the stresses. So sigma A, as you can see, is center, the x coordinate of the center. So I'll call that center x plus the radius, which is 20 plus 65, and so that's 85. And then the diameter, well, the other part, the other stress, the minimum stress here is center x minus radius, which is 20 minus 65, which is minus 45. And everything here is in MPa. So MPa, MPa. Okay, so we know sigma A, sigma B. This is a plane stress condition, which means that the third stress is 0. So we have the principal stress, the maximum stress is 85. The next one, the intermediate one, is 0, because in this case, plane loading, the third stress is 0. And then the minimum one is sigma 3 is minus 45. I wrote this in this fashion because that's how we developed the theories, right? Okay, so we have the stresses. Now we can go ahead and apply each of those two theories. So let's talk about the maximum shear stress theory. Okay, so if you ruffle back, you will see that. So let's do maximum shear stress. Okay, so the formula for the factor of safety, I can write the definition. It's max stress divided by the allowable stress. And so the max stress, I wrote it down as tau prime max. And then it's tau max is the allowable shear stress. Here we have replaced stress with shear stress because this is the maximum shear stress theory. So then the question is, what's tau prime max and tau max? So tau prime max is the shear stress which is developed when you take the material and load it in tension. And when the material is about to fail, that's when you'll get tau max. So that happens when the strength is Sy, but that's the strength in tension, right? You need to find the stress at an angle of 45 degrees, and the stress at 45 degrees is half of Sy, and that's why I got it. So the derivation was done earlier. Just trying to remind you of how we did it. Okay, so that's Sy divided by 2, and I think Sy is given to us. It's 250, thanks. So it's 125 overall. Okay, and then tau max. Okay, so tau max is the stress in the given loading condition for the stress element I just showed you. So that stress, that's the maximum shear stress, can be computed from the principal stresses. It's basically sigma 1 minus sigma 3 divided by 2. And we just wrote down the previous page these two values. Sigma 1 is 85 and sigma 3 is minus 45. So 85 minus 45 divided by 2 comes out to be 65. So from this formula, we can now write the factor of safety is 125 divided by 65, which is 1.92. And so our factor of safety using the maximum shear stress theory is 1.92.
that tau prime max, like it's not, it would not always be SY over 2.
It's always SY divided by 2. So it's like this. If you have the specimen, you load it with a stress, eventually it fails. The failure occurs at 45 degrees. What is important? And that stress at 45 degrees is SY divided by 2. That's why we use it. Okay, let's go by the distortion energy theory question. How did you know sigma 2 is 0? Yeah, so let's go back. Okay, so this is a condition of plane stress. In plane stress, there are two stresses are non-zero. The third stress, one stress is always 0. The other two stresses can also be 0. So in a plane stress condition, if you see here, sigma x is 80, sigma y is minus 40, and then sigma z, which I have not shown here, is 0. So that stress manifests as sigma 2, which is basically 0. You'll always get one stress equal to 0 in plane stress. You could have more stresses 0, right? You could also have sigma 2 0, in which case you might see another stress being 0, but one is always 0. And I just arranged them in such a way that sigma 1 is greater than sigma 2 is greater than sigma 3. That's the rule in which you arrange it, so that you can then use the failure theory. So let's do the distortion energy theory. Okay. Now in this case, what you need to do is you can use, well, there are two formulas. One is you could use the von Mises in terms of, you could use the von Mises in terms of sigma A and sigma B. Or you could also, you don't really need to calculate the principal stress. You can also use this one. Same answers. Okay, so here, I think I used the first one. Again, you can verify with the second one. Okay, so using this, you get sigma prime equals 114.35. Okay, now when you compute the factor of safety, again, the same definition, max stress divided by allowable stress. Now, the stress you apply here, max stress, is going to be different from the max stress for shear. That's because when you're looking at distortion theory, the max stress comes from a uniaxial test, right? You do a uniaxial test, and when it fails, it's SY. And then you compute the von Mises stress here. So the von Mises stress is SY squared plus 0 minus 0 times SY, right? I just put the values here. And so the max stress when failure occurs is SY. So on the numerator, we will have SY, and the denominator will have this sigma prime. So that's the sigma max. So then using this theory, SY is 250. And sigma prime is 114.35. And so N comes out to be 2.18. Okay, so the thing to note here is we computed the factor of safety using two failure theories. We used distortion energy theory and maximum shear stress theory. We found that the factor of safety is greater for distortion energy theory than it's for maximum shear stress theory. Okay, so let's do a problem related to Coulomb-Mohr because that's like a, yeah.
So you're saying if we plug in 80 and 40 to the sigma x, sigma y, we'll still get 114.35?
Yes.
Okay.
Did you check? Yeah. You can check, yeah. Because the way this is derived is actually putting that formula, principal stress formula in sigma A is sigma x minus sigma y square and so on. Get the left right there.
You added some things like the top extent bit, like at like the top by the top, when you go sigma x and sigma y by like the first drawing.
So you didn't get this one?
No, 4.
Say that again.
But go back to like the actual like problem.
Oh, problem. Okay.
There's something like, okay, yeah. Oh, like this C.
Yeah, sigma z is 0.
Yeah, that's what I was like. Okay.
Okay, let's do next problem. A 250 millimeter diameter shaft is statically torqued to 230 Newton meters. It is made of cast 195T6 aluminum with a yield strength in tension of 160 MPa and in compression of 170 MPa. It is machined to final diameter. Estimate the factor of safety of the shaft. Okay, so here you are given this critical information that the strength in tension is 160, strength in compression is 170, and that should ring a bell that the stresses are different, which means that you probably you cannot apply the maximum shear stress and distortion energy theory because it doesn't really account for that. Okay, so the diameter is 25 mm. And it looks like the torque is 230 Newton meter. Okay, so what do we know about Max Coulomb-Mohr theory for a torque loading condition? I did it last time. I talked about factor of safety. So this is Coulomb-Mohr theory. Right, let's see what we want to compute, and then we'll figure out what other formulas we need. So Coulomb-Mohr theory says that sigma 1 divided by st minus sigma 3 divided by sc equals 1 divided by n. So n is a factor of safety, and that's the formula for a generic test where you have sigma 1 and sigma 3 are the principal stresses. Now,
That's sigma 1 and sigma 2.
Sigma 3. Now for pure shear, and I say pure shear because it's only loaded by torque and not by a bending moment or something else. So for pure shear, we have sigma 1 there will be a max tau, right? And so it will be something like this. Okay, so you can draw the Mohr circle for this. It's pretty simple because it will be a circle centered at 0, 0. This will be tau max. This will be minus tau max. So we can see that this principal stress is sigma 1. The minimum is minus tau max. And so we can put that back in this equation and write tau max divided by st minus tau max divided by sc equals 1 divided by n. So what we can do here is we can move things around and write a formula for well, so simplify, and I will skip the steps but you can verify that you can find the factor of safety to be STSC divided by ST plus SC, and then you need to multiply this by 1 over tau max. Okay, so we have pretty much derived a formula for pure shear using Coulomb-Mohr theory. We only need to now sub in the values for ST, SC, and tau max. So it turns out that if you see this, we are given ST and SC, so these are known. We only need to compute tau max, and tau max can be found based on the fact that the shaft is loaded in torsion. So there's a formula which relates tau to torque, right? Tau is T times the radius, because the maximum shear stress occurs at the circumference of the shaft, and the stress decreases linearly to 0 at the center. TR divided by J, T times R. The polar moment of inertia for a solid shaft is something which will give you pi r raised to 4 divided by 2, and so this is T times 2 divided by pi times r cube. Okay, so by the way, this is tau max because I put the radius in my equation.
Wait, you have like R4 and one, R3 and another.
Yeah, there's an R up here, and there's an R4 down here, so it cancels and you get. So from this, tau max equals two times the max, the torque is 230. Pi times the diameter is given, it's 25 millimeters. So 12.5 divided by 1,000 to convert that to meters.
12.5, how do you get that from 25?
Half of, so radius is half of the diameter. Okay. But then I need to convert that to meters, so that's 1,000. So from this, tau max comes out to be 75 MPa. The last thing left is to take this formula and sub in the values, right? N equals ST is 160 and 160 and 170. So 160, 170 divided by 160 plus 170 times 1 divided by 75. So since all the units are in MPa, I don't really need to convert anything. It all will work out non-dimensional. That's the answer. Okay. Okay, let's move on. Okay, so here is a sort of an applied problem with the real system, and we need to find uh, a certain force, in this case F, such that it won't fail. So force F is applied at D as shown. Assume that the material is ductile and the critical point of failure is A. So it's right here. Compute the value of F, assuming maximum shear stress theory, distortion energy theory. Assume that the yield strength is 81 kTSI. Okay, so clearly there's a force F. This force, as you keep increasing it, some part will fail, and you're told that the failure will occur at A. And so we need to limit the F such that it never really reaches that critical value for failure. Okay, so first of all, the question you want to ask is, what's going on A? What are the stresses at A? Because unless you have the stresses at A, we cannot apply any of those theories. So if there's a force F here, you can see that this part of the beam is subjected, or this part of the shaft is subjected to a bending moment, right? And the bending moment M will be this force F times this distance, 12 plus 2, 14. So clearly, if there's a bending moment, there will be a shear stress. Sorry, there'd be a normal stress, leads to this 12 and this 2. So that's the moment arm. So this force will give you that moment arm sigma. Okay. There's something else going on, which is because there's a force F, and this force F has a lever arm of 15-inch, you will see that it's actually also loaded in a torque, right? There's a torque which is acting along this axis. So the torque is going to be the force F times the lever arm, which is 15 now. So this will leads to tau. Okay, so if we take A, this point A, we can actually draw the stresses. There'll be a stress in the x direction. So it's tau sigma x is a question. Torque and a moment. Torque leads to rotation. Leads to rotation. M leads to in this is more like a bending thing. Bending. So this is going to, so the shaft or this piece from A to C will bend due to M, but then so A to B, but then A to B will also be torqued due to this force. So bending is in this plane, in the plane of A. Well, it's in the axis is normal to AB, and here the axes are along AB. Okay, so here the stress sigma x, sigma y. That sigma y is going to be 0 because the bending moment doesn't really enforce that. So this is not going to be y, it's going to be z. Because the z direction is shown in that direction. And then there'll be a shear stress like this. Tau zx. Okay, and then tau xz is same as tau zx. So we need to find sigma x, tau zx. And once we do that, we can apply the theory. Let's find those stresses. Okay, so sigma x is my divided by I. So as I said, m is f times 14. Y is the distance from the neutral axis. So the shaft, the neutral axis, that's going to be y. And so maximum stress occurs at the top part. So if this is A, it'll occur right. A is in the surface, so it's going to be at d divided by 2 divided by the moment of inertia that will be given to you. It's pi d raised to 4 divided by 64. So simplifying this gives me 142.6 F, where D is, well, the D is, if you can go back. So here there is, where's the diameter? This is 1.5 inch for the outer part, and the inner part is going to be 1 inch. Okay, and the critical stress will occur the smaller diameter. That's the one which will fail. That bigger the diameter, the less is the chance of failure, because you've seen as the diameter increases, the factor of safety also increases. So that's the one which is going to fail. So I used D equals 1 inch. In this formula, right? And then once I put the value for D, I can solve for sigma x in terms of capital F. Then, as I said, there's tau zx, and that comes from the torsion formula, T times R divided by J. So the torque, I wrote it on the previous page, it's F times 15. R is the radius, it's D divided by 2. The polar moment of inertia will be given to you. It's pi d raised to 4 divided by 32. And again, if you do the same, plug in the value for D is 1 inch, you get 76.4 times F. Okay, so we've got the stresses, and now it's time to apply the stress theory. So pretty much what we got here comes from things we've learned in the previous sections, right? There's nothing about failure theories yet. It's now is where the failure theories comes, and now what we're going to do is very much similar to what I did in the problem 1. Once you identified the stresses, it's a matter of applying the same formulas as before. So let's do a maximum shear stress theory. Okay, for that I need to find the maximum stress, and I'm going to go by the formula sigma x minus sigma z divided by 2 square plus tau xz or tau zx square, whatever you like. They are complementary, so it will be the same. So sigma z is 0. I think I believe I have it here somewhere. So sigma z here is 0, so I put 0. Okay, so subbing in the value. So now the values here are in terms of F, right? We have tau zx here, sigma x here, and so I get 104.5 F. Okay, for failure, tau prime max, we know is sy divided by 2. That is, well, sy is given to us. It's 81 kpsi. So I'm going to convert that to psi, and that comes out to be 1. You need to multiply by 1,000. Okay, and so I can simplify this, but let me just write the formula for factor of safety. It's n equals the maximum stress divided by the stress we get from the stress element we drew. So we have 81 times okay. So I don't have a factor of safety, right? Yeah, let me do that. But hold on, I don't have a factor of safety. So here it's assumed that there's no factor of safety because it's not given the problem. So it basically what it means is that this thing fails when the maximum shear stress is reached. So the factor of safety, in other words, is 1. Or let me just write it. That's a better way to write this is tau max is greater than equal to tau prime max is when failure occurs. So factor of safety is 1 here. So we can write, we'll take the equal to sign and write 104.5 F equals 81 times 1,000 divided by 2, and then that gives us F equals 388 lbf. Okay, so that's 388. That's from the maximum shear stress theory. Let's do distortion. Distortion. Energy. So here, well, I need to find the von Mises stress. So the formula is sigma x squared, sigma, in this case, z squared, minus sigma x sigma z plus 3 times tau zx squared. But sigma z is 0, so that 2 of those things cancel off. And if you sub in the value for sigma x and tau zx in terms of f, we get 194.5 f. Again, for failure, sigma prime should be greater than equal to the strength. And so we have 194.5 is equal to, so taking the equal sign, 81,000, we get F equals 416 lbs. Okay, question. Okay. What value did you use when you solve for sigma x in the beginning? Yeah, that's right. Thanks for answering that question. It is it is d equals 1 inch. So I have it here. That went in here and I got F, and the same D went here. Okay, so here we have computed the force F. And something to note here is that we found that the force F is in distortion energy theory is greater than the force due to maximum shear stress theory. And that is because distortion energy is less conservative compared to a maximum shear stress theory. That's why you get a higher force, which you can apply given the distortion energy theory. Could you go over how you knew that there will be bending and torque at A? Absolutely. So if we go over here and look at element A or point A, what we need to think about is what is the effect of F on A, right? So F, this force F will cause this arm to rotate. So in other words, there will be a torque like this. That torque is going to cause shear stress here. Then this force is also, so this force here is the same as applying a force here. That's going to bend this rod. So if you think of this shaft, this force is now acting this way. So this is going to bend this rod. And so this F will cause a bending moment M. So the torque comes because of F times 15. And this M comes because of this force, which can also be treated as a force over here, times 12 plus 4, so 14. Okay, so this is the final problem, and this is one of the problems which I wanted to intentionally put here because it's more of a design problem than anything else. This actually is incorrect. This should have been, so it's dt, so this is d times d. Okay, so I'll set up this problem and I'll sort of put things on paper, but I'll fill the dots a little bit later. The shaft shown below is subject to a force F. Okay, so this force, an axial load P, a torque T. The material used is aluminum with a yield strength of 276 MPa. Using the table shown below and a design factor of 4, select a stock size for the shaft and compute the factor of safety. assume one misses stress as the failure criterion. Okay, so there's a lot of things going on here. So we have this shaft, and the shaft is characterized by two numbers. One is the diameter, and the other one is the thickness. So those things are given here. Okay, so given a diameter and thickness, there's a mass because the length is 120 mm. There's a cross-section area. There is a moment of inertia. There's, I think, a spring constant. This is not going to be used in our table, in our calculation here. Section modulus and polar moment of inertia. So it's basically, they have computed all these values for the stock size. So you do not need to do that work. What we need to do is we need to understand what are the stresses at A first. Then we'll apply the maximum shear stress theory, sorry, the distortion energy theory, compute the critical value for the stress, right? And the stress can only be computed once you provide a stock size. Once you provide a stock size using these numbers, we'll be able to compute the von Mises stress, and that will be used to figure out which of these material is not going to fail given this particular yield strength. Okay, so what we do is we first identify the stresses at A. Yeah, I think I should do this a little bit slowly. So what I'll do is I'll set down the things I'll be doing, and if you want, you can go home and try it yourself. But I'll finish this problem next time, but I think it's important that I solve this slowly in the class. So this is what we'll do. First, find stresses at A. Okay, so that will be normal stresses, shear stresses. Find von Mises stress for the given loading and assuming a stock size. So every time you assume a stock size, you'll get a von Mises stress. Then final step is use the yield strength of 276. Yield strength of 276 MPa. Factor of there's a design factor which is I think 4. Yeah. So use the yield strength, the design factor of 4 to pick a stock size in 2. That is for, so when you do this step 2, you will find that the von Mises stress actually exceeds that of 3. If it exceeds, then you need to choose the next size. And you keep doing that till you find a stock size which will give you acceptable strength so that it will not fail in this von Mises stress criterion. Compute the maximum allowable stress. Okay, so we know the definition of design factor is max stress upon allowable stress. So the max stress is our yield strength, and let's say that the allowable stress is sigma A. Okay, just give it a name. So ND is 4, SY is 276, so 276 times 10 raised to 6. Divided by sigma A. We can solve for sigma A, and that comes out to be a quarter of 276. So it's 69 times 10 raised to 6 pascals, or if you like, it is the same as 69 MPa. So we found the allowable stress. Now what we need to do is we choose a stock size. We'll find the von Mises stress for a stock size, and we need to see if that stress, the one Mrs. stress for that stock size is less than sigma A 69. If it's less, it's good to go. If it's not less, then we need to choose the next stock size and so on. Right? That's what we'll do. So let's find the one Mrs. stressed. So let's compute sigma prime. Okay, to compute sigma prime, we need to first understand what are the stresses in this shaft. So I can redraw it here. There is P, P, F, and a torque. And then the critical section here is A. So right there. So if you draw A, and then the convention here is x-axis is this way, y-axis is upwards, and the z-axis is this way. Okay, so there will be a stress in this direction, sigma x. This is, by the way, A. Okay, this stress will be due to the bending moment F. Okay, the bending moment always leads to a stress in the axial direction. And then the stress P, the force P will also induce an axial stress. So sigma x is going to be F times, there's a moment arm here. If you want, let's call that L. So F times L, that's the moment, times the distance from the neutral axis. The neutral axis will pass through the center. And so that distance is going to be the radius. So diameter divided by 2 divided by I. So that's the piece due to force F. There will be another piece for another contribute. The force P will also contribute to the stress. So that force P is an axial force. So P divided by A is going to be the axial stress, and this direction is going to be again the same direction as sigma x. Okay, and so we know that sigma x is that, sigma z is 0. There's no stress in that direction. And then there will be a shear force like this. Sorry. Tau zx. And that shear force will be induced due to the torque T. So we can write that formula based on our equations for torque. So the equation is the torque times the radius. So here the radius is due to torque, or it's abbreviated as T. Okay, so T times R, and R I wrote down as half of the diameter, and then there's J. Okay, so let's sub in the values. F, as we know, is from the previous page, F is 1.75 into 10 raised to 3 newtons. The length L is 120 millimeters, so it's 0.12 meters. Diameter is unknown, so I'll keep it as it is. It's 2 times I plus P is known, it's 9 kilonewtons, so 9 times 10 raised to 3 divided by I. And then the torque P is given to us, it's 72. Diameter is unknown, 2 times I. That is the question. Okay. Well, why did we use D? It's the radius. Okay, looks like it was cleared up. Yeah. Oh, yes, that's right. It's not I, it's A. Gotcha. We can try to simplify this. I don't quite have this. So it's 1.7.
So you just bring the like
Values.
divided by 2 for the radius and just put in the denominator.
Yeah, just move that to the denominator, right?
Or like if we're just dividing the d divided by 8, we're just dividing the diameter by 2 to get the radius. Like if you put it in the denominator like that, wouldn't that also mean you're dividing the torque?
Yeah, it's fine. I mean, so I just you could divide the torque or you could keep it as it is. This 2 goes down. That's what it is. Okay, so I'm going to write this down. Simplify this and write it down. Sigma x I get as 105 divided by I, and then the other one is 9,000 divided by A. Is that right? And then 72 divided by 2 is 36. By J. I get that right. Oh, so my bad. This should be J. Thanks. Okay, so that's the stress. Now, the one misses stress, sigma prime, and this is a formula I'm going to.
Got the d in both.
Did I? Yeah. I don't know what I'm doing today. So D plus D. Good catch.
And the 2. Oh, is that like
I'm missing something. D, there's no D there. There's D here. There's D here. Okay, so my bad. Looks good. Here's the D. Okay.
I assume that you were just gonna like take the d out and make it just kind of like take out a
Oh, you could do that way too.
but then there isn't a d in like the second part there. So
In area? You mean here?
Sure, you could take it out of that, but
yeah, but you wouldn't do that. I'll show you why. You would keep it as A, and you'll keep the D as it is. I'll show you in a bit why. So the one versus stress. This is a formula you can refer to. Is computed from the stresses sigma x and tau zx as 3 times sigma x squared plus tau zx squared. Okay, so what you can do is you can sub in the value of sigma x from here and tau zx. Now, what you need to do is the following. You need to see these formulas, as you can see, depend on D, depend on I, depend on A, and then J, right? These 4 numbers, D, I, A, and J. So what you need to do is go back to the table. You see there's a A, there's a I, there's a J, and there's actually a D sitting in here. This is D. So what you'll do is you'll pick D, you'll put in the value of A, put in the value of I and J, and then compute sigma prime. You do this, compute sigma prime, see if it's less than our computed value here. The maximum stress allowed is 69. So it should be less than 69. If it's less than 69, you're good to go. And so what I did was, instead of doing it each time and checking, I just did a brute force thing, which is I just computed it for all these dimensions given in this formula. So from table, compute sigma prime using values of D, I, A, and J. And so that table, I have it here somewhere. Then copy this. So I did this in did this in MATLAB, but you can use Excel, for example, to do it. You don't need to interpolate the values here because it's just that you need to pick a stock size. There's no interpolation involved here. Got. Okay. Okay, so it's clear. So I just pretty much computed sigma prime. Let's say this is formula 1 from the table by putting in A, I, J, and of course D. So you can see these are the stresses. And I'm looking for a maximum stress of 69 MPa. So 69 MPa came from my factor of safety. This is the maximum stress the shaft can bear before failure. So 69 MPa is my max. So I see that this is 1740 times 10. So this is 1740 MPa, 179, 712. So it's still higher than 69. You reach here, you see it's 71, which is still higher than 69. So it's really this value which is acceptable. This is the highest value on the stress can be accepted without the material failing. This is less than 69 MPa, and which means that, or which is sigma A. So we can choose this stock size. Choose this stock size. So diameter is 42 mm and thickness is 5 mm. Okay, so last question. So this was finding the stock size, which is part A. Part B is asking to find the factor of safety, which is the max stress upon allowable stress. So the max stress is 276, which is given to us, and the allowable stress now we've computed it. It is 60.42. So the factor of safety is 4.56. So you can see that the design factor is 4, but the factor of safety is gone up 4.56 because there is no stock available which will give exactly 69 MPa. You don't have a material which will be exactly 69. We have something which is less than 69, and that's why the stress has, the factor of safety has gone up. Okay. So this is a type of question you might expect to solve when it comes to design. There's a table, stocks to choose from, which one you go for.